This chapter will first of all show you the role sensors play in motor vehicles by using the pre-safe occupant protection system as an example. It then goes on to demonstrate by means of another example how sensors work in principle. Creatures like this cat use their sense organs to perceive their environment and their own behavior, and are therefore able to react appropriately in every situation. In the motor vehicle, this is the job of sensors. In a similar way to the sense organs, they register the vehicle's environment and operating conditions. From this information, the control modules determine the appropriate actions to take. An example of the complex interaction between sensors is the pre-safe occupant protection system. It uses the vehicle data and activates the vehicle's protection systems as a precaution in hazardous situations. In doing so, for example, the occupant's seating position can be optimized by means of the luxury seat and the restraint system. This has been made possible by networking the active and passive safety systems. The vehicle is thus able to assess complex situations more effectively. What is the basic task of sensors? To answer this question, here's an example. A temperature sensor registers the temperature of the coolant. It consists of a temperature-dependent resistor through which an electrical current flows. If the coolant temperature changes, the resistance of the sensor will change accordingly. The control module's electronic analysis system uses this to determine the corresponding coolant temperature. The information is displayed in the instrument cluster and may trigger an intervention in the fan control system, for example. Thanks to the example on the previous page, you've now learned the basic task of sensors. It is the conversion of a physical or chemical variable into electrical signals. Let's summarize the chapter again. Using the pre-safe occupant protection system as an example, you have learned the importance of sensors in motor vehicles. Taking the example of the coolant temperature sensor, you have also been able to follow how sensors basically work. Their task is to register physical or chemical variables and convert them into electrical signals. These are then forwarded to an electronic analysis system. This chapter deals with the various fields of application of vehicle sensors. After a general overview, you will be given examples of different sensors from the following areas: safety, environment, vehicle operation, and comfort enhancement. Modern motor vehicles have a large number of sensors. They are indispensable for many open and closed-loop control functions in the different vehicle systems, in areas such as safety, environment, vehicle operation, and comfort enhancement. On the next few pages, you can take a closer look at some sensors from the different fields of application. Safety and occupant protection are number one priority in a vehicle. Sensors have an important role to play in this regard. Let's look at a passenger car by way of example. A driver is travelling along in his car. During the journey, the pressure in the left rear tyre starts to decrease slowly because of a leak. The wheel sensors in the wheel rims register the air pressure and temperature and send this information at regular intervals by radio frequency transmission. The tyre pressure monitoring system control module receives the data via the wheel antenna. If the tyre pressure drops quickly or is 0.4 bar below the set pressure, a warning message will appear in the multifunction display of the instrument cluster. Let's assume that the driver hasn't taken any notice of the message in the instrument cluster and continues on his journey. A short while later, the vehicle drives into a curve at excessive speed. The driver brakes too late and the vehicle becomes unstable. The various sensors in the Electronic Stability Program, ESP, send their measurements to the control module, which immediately detects the hazardous situation. Selective brake pulses are used to restabilize the vehicle. What happens, however, if the vehicle gets into a situation where a collision is unavoidable? Here other sensors, such as the frontal acceleration sensors, come into operation. These measure the deceleration of the vehicle and trigger the deployment of the various occupant protection systems, depending on the severity of the collision. These occupant protection systems include the seatbelt tensioners of the restraint system, which are activated in several stages, and the airbags, which are also deployed in several stages. Vehicle theft prevention is another safety application in which sensors are used. The inclination sensor of the anti-theft alarm system, or EDW, for example, determines the position the vehicle was in when it was parked. This is stored in the control module. Any change in the current position is registered by the inclination sensor, and the control module triggers the alarm. Vehicle sensors are also used to protect the environment, ensuring that it is not excessively polluted by the operation of the vehicle. One example are the sensors in the exhaust system, which analyze the composition of the exhaust gases. In a gasoline direct injection engine, for example, 2 oxygen sensors, one upstream and one downstream of the 3-way catalytic converter, and a nitrogen oxide sensor located downstream of the NOx absorber are responsible for analyzing the composition of the exhaust gases. The values measured influence the engine control system to prevent the emission of harmful exhaust gases. In modern vehicles, sensors are essential for vehicle operation. The crankshaft position sensor, for example, and the camshaft Hall effect sensor provide information on the sequence of the engine's working strokes. Without these and other sensors, an optimum control of the engine would be inconceivable. Another important task of sensors is to monitor the operation of the vehicle and adapt this operation to the measured operating conditions. The charge air pressure sensor, for example, measures the current charge air pressure in the intake manifold. This information will influence the engine's charge air pressure control and injection quantity control, amongst other things. Without sensors, it would not be possible to have many of the comfort features in the vehicle. One example are the various temperature sensors for controlling the air conditioning system. Amongst other things, they determine the temperature of the outside air, the temperature at the evaporator, the temperature at the heat exchanger, and the temperature in the passenger compartment. Without this temperature data, you could not regulate the air conditioning system to enhance comfort. Let's summarize the chapter again. Sensors are indispensable for many closed and open-loop control functions of the various vehicle systems. They are used in virtually all areas of the vehicle, such as safety, environment, vehicle operation, and comfort enhancement applications. In this chapter, you will learn about the different types of sensors. Sensors can be divided into the following types, depending on how they are structured and the components they consist of: switches, passive sensors, active sensors, intelligent sensors, and complex sensors. The following pages will show you how the individual types of sensor differ from each other. One of the simplest forms of sensors is the switch. Switches respond to external conditions and just supply on and off information. The position switches of the Vario roof are one such example. They register the position of the roof when it is opening and closing. Have a look, for example, at the switch on the hinge of the boot lid. As soon as the switch is closed, the control module receives a ground signal, and from this knows that the boot lid is fully open. Passive sensors change one of their electrical variables when influenced by a variable acting from outside. This is the case, for example, with temperature sensors, which have NTC resistors. When a test voltage is applied, a current is generated which flows through the NTC resistor. Its resistance changes with temperature, thereby causing a change in the current being measured. The control module registers this change and responds accordingly. NTC resistors are used to measure temperature. For example, the temperature of the outside air, the charge air, the coolant, the engine oil, or the fuel. Have a look yourself at what happens when the temperature rises. The higher the temperature, the higher the measured current flowing to the control module. If the temperature exceeds a specific limit, the control module responds with an appropriate control action. In addition to passive sensors, there are also active sensors. You can recognize these because in addition to the signal line to the control module, they also have additional lines for power supply. Many of these active sensors are Hall effect types. They include, for example, the camshaft Hall effect sensor and the accelerator pedal position sensor. Intelligent sensors have their own electronic analysis systems, which register the sensor signal and process it in such a way that the actual variable is shown unadulterated. One such example is the hot film air mass sensor. It calculates the air mass drawn in by the engine. It does this from the cooling of a sensor element which contains a heating resistor. However, this is only possible if the electronic analysis system is, at the same time, responsible for the controlled heating and temperature monitoring of the heating resistor in the sensor element. The control voltage required to heat up the resistor is used by the control module as a measure for the intake air mass. Complex sensors are designed for special tasks. Like the intelligent sensors, they also have their own electronic analysis system. However, complex sensor systems consist of several sensors, and only together do these sensors supply a usable overall measurement result to the control module. One example of complex sensors is the radar sensor of the Intelligent Autonomous Cruise Control with 3 transmitting and receiving units. These units use the echo principle to measure the distance from the vehicle ahead at different angles. Another example of a complex sensor is the oil sensor. It consists of a capacitive measuring element and a temperature sensor. This can be used to measure the oil level, oil quality, and oil temperature, thereby giving the control module a comprehensive picture of the condition of the engine oil. Complex sensors usually transfer their information to the control module in digitally processed form. Let's summarize the chapter again. The simplest form of sensors are switches. They just supply on and off information. Passive sensors change one of their electrical variables in response to the influence of a variable acting from outside. Active sensors have the actual signal line to the control module plus additional power supply lines for operation. Intelligent sensors have their own electronic analysis system, which processes the measured values before forwarding them to the control module. Complex sensors also have their own electronic analysis system. In contrast to intelligent sensors, they consist of several sensors, and only together do they supply a usable overall measurement result to the control module. This chapter provides an overview of the main physical variables which are registered by sensors in motor vehicles. These include position sensors, which register travel and angles in the vehicle, force and pressure sensors, acceleration sensors, temperature sensors, light sensors, sound sensors, and sensors for measuring quantities and composition of substances. When measuring a position, that is, when registering travel and angle information, often only specific limit positions or intermediate positions are required. Mechanically actuated switches are used, amongst others, for this task, as is the case for detecting the limit positions of the vario roof. In addition, there are proximity switches, for example, reed contact sensors or transponders. As an example, let's have a closer look at the operation of a reed contact in a lorry fuel level sensor. This consists of a printed circuit board through which current flows. On the printed circuit board, there are a large number of reed contacts and resistors, arranged in pairs. In addition, a float with a magnet in the fuel level sensor tube moves along the printed circuit board past the reed contacts. The reed contacts themselves consist of a glass tube filled with inert gas, into which are sealed 2 magnetized contact blades. As soon as the magnet's magnetic field starts having an effect on the contact blades, the contact closes. Depending on the position of the magnet in the sensor tube, another reed contact will be switched. The contact blades open again as soon as the magnetic field is removed. The current flows over a number of resistors, the exact number depending on the position of the float. The control module calculates the fill level from this and displays it in the instrument cluster. The continuous registering of positions in millimeters or angles requires sensors which can register the entire measuring range. Rotary resistors, which are also called potentiometers, are a simple example for continuous distance acquisition. They're used, for example, to calculate the level of fuel in the fuel tanks of passenger cars. A potentiometer consists of an electrical resistor which is divided into two resistor areas by a moving sliding contact. The sliding contact on the fuel level sensor is connected to a float by means of a lever. A different resistance is produced on the resistor track, depending on the position of the float. This is registered and evaluated by the control module. Another important group of sensors for the continuous registering of travel and angles are the Hall effect sensors. These sensors are often used for registering the accelerator pedal position, for example. The Hall effect sensor contains a thin semiconductor chip. A supply voltage is applied to this, which results in a flow of current. If a magnetic field then acts vertically on the chip, the electrons are deflected by the magnetic field. This is known as the Hall effect. Lines located at the side pick off the resulting Hall voltage, which is dependent on the intensity and direction of the magnetic field. When the accelerator pedal is pressed, a permanent magnet moves around the Hall effect sensor. The control module calculates the position of the accelerator pedal from the Hall voltage. Hall effect sensors are also used to register the position of rotating shafts. This is the case, for example, with the camshaft Hall effect sensor. The sensor consists of a permanent magnet, a semiconductor Hall element, and an electronic analysis system with electrical connections. The magnetic field of the permanent magnet penetrates the Hall element and in so doing generates a measurable Hall voltage. A toothed segment on the camshaft, from which it is separated by an air gap, moves past the sensor. As you do, observe the voltage signal which is sent by the sensor's electronic analysis system to the control module. As soon as the toothed segment intersects the magnetic field, the field intensity of the magnetic field changes. This causes a change in the Hall voltage. The electronic analysis system in the sensor amplifies the Hall voltage so that the sensor signal jumps from the supply voltage to 0 and vice versa. This signal is used by the engine control module to distinguish between the compression stroke and the exhaust stroke. This and the signal from the crankshaft position sensor are used to synchronize the firing and injection order. In addition to Hall effect sensors, there are also other sensors which can be used for registering the rotation of shafts. Inductive sensors, such as the wheel speed sensors or the crankshaft position sensor, are one example. Let's have a closer look at the crankshaft position sensor, for example. It consists of a permanent magnet, a soft iron core, and a stationary coil. The sensor is located on the engine housing and is separated from the flywheel by an air gap. The flywheel may have teeth or, as in this example, grooves located at regular intervals. The rotational movement of the flywheel generates a waveform voltage signal in the coil, caused by the periodic variation of the magnetic field. This is used by the control module to determine the exact position of the crankshaft and to calculate the engine speed. Other sensors used in vehicles for continuous position registering include plunger coils and differential transformers. These sensors include, for example, clutch travel, gear, and gate sensors. By way of an example, let's have a look at a gear sensor for a lorry transmission. This is a plunger coil type sensor. It consists of a coil and a moving iron pin. The coil is cycled by the control module. The voltage builds up in the coil and then drops again in accordance with this cycle. In general, the higher the inductance of a coil, the longer it takes for the voltage to keep up with the applied signal. If the coil has an iron core, the inductance increases considerably. This relationship is used for the gear sensor. Depending on which gear is selected, the iron pin is located at a greater or lesser depth in the coil. The deeper it is, the greater the coil inductance, and the longer the voltage build-up takes. For each cycle, the control module measures the time it takes the coil to build up the voltage completely. From this, it calculates the position of the iron pin in the coil, and from this, in turn, it is possible to determine which gear is selected. Finally, there are the sensors which register the position of the vehicle. These include the inclination sensors. One example is the inclination sensor for the anti-theft alarm system, which is located in the control module housing. The sensor consists of an enclosed housing which is filled with an electrically non-conductive fluid. Protruding into the fluid are two metal plates which together form a capacitor. The capacitance of the capacitor is increased considerably by the fluid between the plates. If the vehicle's angle of inclination changes, this causes a change in the immersion depth and thereby in the capacitance of the capacitor. The tilting action changes the immersion depth of the metal plates in the fluid. An electronic analysis system in the sensor registers the corresponding change in capacitance and sends the angle of inclination calculated from this to the control module of the anti-theft alarm system. This then triggers the alarm. Various measuring methods are used to measure force and pressure in vehicles. For example, force-sensitive resistors, the FSR sensors as they're known, can be used for measuring forces. They are used for seat occupancy recognition. An FSR sensor consists of three components: a carrier film with electrodes and electrical connections, a spacer film, and another layer of film with the FSR semiconductor layer. The sensor mats incorporated into the vehicle seats contain a number of FSR sensors connected to each other. They supply their measurements to an electronic analysis system. If a seat is occupied, a force will be acting on the FSR layer and brings this into contact with the electrodes underneath. Try it out by dragging the weights in turn to the FSR layer with your mouse. As you do so, observe the display of the ohm meter connected to it. The force acting from above exerts a load on the FSR layer and brings it into contact with the electrodes. The higher the force, the more electrodes are contacted. As a result, the resistance measured at the connections drops. The electronic analysis system detects from the measurements whether a seat is occupied or not, and forwards this information to the restraint system, for example. Another way of registering force and pressure changes is by utilizing the deformability of materials. One example of this are the wire strain gauges, like those used, for example, in the charge air pressure sensor, the common rail pressure sensor, or the ESP brake pressure sensor. Let's have a look at the charge air pressure sensor by way of example. It essentially consists of a housing from which the air has been removed, a glass base to which a silicon diaphragm has been attached, plus electrical connections. The charge air pressure acts via a duct directly on the sensor diaphragm. The diaphragm is deformed in different ways depending on the level of pressure. The strain resistors contained in the diaphragm change their electrical resistance as a result of the mechanical loading. The sensor signal is used by the engine control module as information about charge air pressure. From a physics point of view, acceleration is a change in the magnitude or direction of speed. Have a look at the lateral acceleration sensor which is used in vehicles for dynamic handling control. Accelerations are measured by a seismic mass being displaced against the restoring force of a spring by the acceleration. The sensor in this example consists of a spring positioned edgewise in the direction of travel and clamped in place at one end. At the other end is a permanent magnet which is attached as a freely moving seismic mass. Above the magnet is a Hall element with an electronic analysis system. When an acceleration acts on the spring mass system at an angle to the direction of travel, the permanent magnet moves from its rest position. The magnetic field of the permanent magnet moves with it and generates a Hall voltage in the Hall effect sensor. The control module calculates the lateral acceleration from this. Vehicle lateral acceleration can also be calculated capacitively. Vehicles are not only subjected to longitudinal and lateral acceleration, they can also be rotational movements around the vertical axis. This type of acceleration can be registered by rotational speed sensors or yaw rate sensors. Many of these sensors are based on a hollow metallic cylinder capable of oscillating, on which piezo crystals are arranged opposite each other. The hollow cylinder is installed in a vertical position in the vehicle and is induced to oscillate each time by two pairs of diametrically opposed piezo crystals. The rotational movement causes the hollow cylinder to rotate with the vehicle around the vertical axis. However, the original oscillation pattern is retained for a certain period of time. As a result, the piezo crystals, which before the rotation were not part of the oscillation pattern, are now induced to oscillate and send electrical signals to the electronic analysis system. These are used by the control module to determine the rotational movement of the vehicle. Another method of determining the yaw rate is the oscillating fork principle. When a vehicle is involved in a collision, sizable negative accelerations occur. The crash sensors forward this data to the restraint systems, for example, or to the central locking control module. They contain piezoelectric materials made of quartz or ceramic. The piezoelectric effect is where pressure or tensile forces act on a material with piezoelectric properties. These forces displace the electrical charges in the crystal lattice of the piezo element. These displacements are picked off as electrical voltage. Crash sensors have bending beams which consist of two piezoelectric layers with opposite polarizations. The acceleration causes the left half to extend. By contrast, the right half is compressed. The electrical voltage resulting from the bending action is picked off at the electrodes. The sensor's electronic analysis system sends the information to the control module. To measure the temperature of air and fluid in a vehicle, sensor materials which change their electrical resistance under the effect of heat are used. Most of these sensors are NTC resistors. Examples include the coolant temperature sensor, the charge air temperature sensor, and various temperature sensors in the air conditioning system. Let's look at the coolant temperature sensor by way of example. The sensor consists of a semiconductor material which has a negative temperature coefficient. This means the resistance of the sensor drops as temperature increases. NTC resistors are therefore also known as negative temperature coefficient thermistors. The drop in resistance as temperature increases is caused by the increased leaching of electrons from the atomic bonds. The higher the temperatures, the more free electrons there are available for current flow. This increases the conductivity of the material. The drop in resistance is registered by the control module and converted into a corresponding temperature value. NTC resistors cannot be used for very high temperatures because the semiconductor structures would be destroyed in the process. Instead, PTC resistors with a positive temperature coefficient are used, as is the case when measuring emission temperatures. PTC resistors consist of a special metal alloy whose resistance increases with temperature. They are therefore also known as positive temperature coefficient thermistors. The increase in resistance is caused by the increase in thermal oscillation of the atoms as temperature rises. These thermal oscillations impede the flow of electrons. In other words, the resistance increases. The increase in resistance is registered by the control module and converted into a corresponding temperature value. In modern vehicles, light intensity is measured for a whole series of open and closed-loop control processes. Luminous intensity is registered with light-sensitive sensors such as photodiodes, phototransistors, and photoelements. Examples where light sensors are used includes the automatic headlamp mode and the automatic brightness control for the instrument cluster display. Have a closer look at the measuring principle of a photodiode using this sunlight sensor for a lorry. A photodiode consists of two different semiconductor layers to which a reverse voltage is applied. This reverse voltage has the effect of allowing only a small amount of current to flow through this diode. However, as soon as light falls on the semiconductor material, electrons are released. The current increases considerably as luminous intensity increases. From these values, the control module for the automatic air conditioner can determine the extent to which the driver's cab is being heated up by sunlight. The combination of a light source, for example a light-emitting diode, a screen and a light-sensitive sensor, together form a photoelectric emitter-detector array. This uses infrared light which cannot be seen by the human eye and which is less affected by the changing light conditions of daylight. Photoelectric emitter-detector arrays can also be used to detect dirt or a film of water, as is the case with the rain sensor. This consists of several optical transmitting and receiving paths in one sensor housing, which is located on the inside of the windscreen. Light-emitting diodes emit infrared light which is totally reflected on the outer surface of the windscreen. If the window is dry and clean, the reflected light reaching the corresponding receiver diode has virtually the same intensity. The water on the windscreen eliminates total reflection and allows some of the light to escape. The photodiode therefore only receives a part of the light emitted by the light-emitting diode. An electronic analysis system transfers the measured quantity of rain to the control module. This then controls the intermittent wipe rate of the wiper system. Sound consists of pressure waves which, for example, dissipate through the air or through solid materials such as metal. Acoustic sensors are used for measuring pressure waves. One such example are knock sensors which register combustion noise in the engine. Let's have a closer look at the measuring principle of a knock sensor. The knock sensor is bolted to the crankcase. The actual sensor element is a ring-shaped piezo ceramic, above which a seismic mass of the same shape is located. The sound oscillations are transferred via the crankcase initially to the seismic mass. Because of its inertia, this seismic mass transfers the oscillations to the piezo element in the form of pressure forces. These forces trigger electrical alternating voltage signals in the piezo element. They're picked off via contact plates and processed further in the control module. Sensors are also used for ultrasonic measurement. Ultrasonic sensors for the parking aid or parktronic function not only as sensors but as actuators as well. This means they can both receive and send signals. Have a look at how such a system works in greater detail. Depending on the model, up to 6 ultrasonic sensors are located in the front bumper of the vehicle and 4 in the rear bumper. The sensor is actuated by the control module and generates ultrasonic signals by means of a piezo ceramic wafer. If the sound waves encounter an obstacle, they are reflected. The piezo wafer receives the echo in a transmission rest period. The control module calculates the distance from the obstacle from the period of time between the signals and sends this information to a display in the passenger compartment. Substance quantity and composition sensors measure variables such as mass, concentration, or density of a substance. One example is the hot film air mass sensor, which registers the air mass flow drawn in by the engine. It is usually located between the air cleaner and the throttle valve. The sensor element consists of a ceramic chip on which different resistors are located. One of these is an electrically heated platinum resistor. A proportion of the intake airflow is led past this resistor and cools it. Immediately next to it is a temperature-dependent sensor resistor which registers the temperature of the heating resistor. The sensor's electronics regulate the temperature at the heating resistor by varying the voltage. If the air mass flow changes, the amount of heat transferred by the heating resistor to the air flowing past it also changes. The electronics detect this change in temperature and readjust the voltage at the heating resistor until the set temperature is reached again. This control voltage is used by the engine control module as a measure for the intake air mass. The oil sensor is another example of how the composition of substances can be measured. This registers, among other things, the water content of the engine oil. Have a closer look at the principle behind this measuring procedure. Two electrodes are submerged in the engine oil. The electrodes act as capacitor plates, and the engine oil between them as the dielectric. The capacitor is part of an electric oscillating circuit in the electronic analysis system. When the engine is operating, small quantities of water vapor penetrate into the engine oil and over time will reduce the lubricating performance of the oil. The water content in the engine oil will, however, also change the oil's dielectric constant. The oscillating circuit in the electronic analysis system registers the occurring change in capacitance and forwards the information as a pulse-width modulated signal to the engine control module. The engine control module can then use this signal to calculate oil change intervals. The condensation sensor in the compressed air brake system of a lorry works in a similar way. Another important variable measured in motor vehicles is the oxygen content in the exhaust gas. This is measured by oxygen sensors. Depending on the exhaust gas concept employed in the vehicle, one or more oxygen sensors will be used. Have a closer look at the simplified basic principle of an oxygen sensor in the following. The sensor consists essentially of two electrodes which are separated by a ceramic layer. The outer electrode is located in the exhaust gas flow. The inner electrode is in contact with the ambient air. When there is relatively little oxygen in the exhaust gas, as is the case when the mixture is rich, there's a big difference in oxygen concentration at the electrodes. The cell outputs a voltage of almost 1 volt. When the mixture is lean, the oxygen content in the exhaust gas is high. The oxygen levels in the ambient air and in the exhaust gas are almost the same. The sensor voltage is correspondingly low. The nitrogen oxide sensor on gasoline direct injection engines works in a similar way, as does the smog sensor in the multifunction sensor of the air conditioning system. Let's summarize the chapter again. Using the main physical variables as examples, you have learned about some of the sensors used in motor vehicles. Specifically, these were position sensors for travel and angle information, force and pressure sensors, acceleration sensors, temperature sensors, light sensors, sound sensors, and sensors for registering quantities and the composition of substances.